Hey, this is OXDF, and today we're doing Advent of Code 2023, day 24, Never Tell Me the Odds. So, we're going to get the positions, XYZ positions and velocities for some starting time, of a snapshot in time of hailstones flying through the air. And um, basically, we need to figure out how many of them, moving only forward in time, will intersect with each other. Will the XY paths cross each other? So it doesn't matter if they cross each other at the same time. It just matters, do those paths cross, and do they cross forward in time, not backwards? Um, so we're gonna do some math. I guess we'll go ahead and dive in. Let's see. I got Day here for day 24, and that will pull my input here and give me a stub to work with. We're also going to grab, let's see, where are you? That is close to you. Let's grab this example input here and put it here. And we'll close that. We'll take a look at the input real quick. We do have 300 rocks, so we need to look at each rock compared to the next rock. So like rock 1 is going to compare to 299 other rocks. Rock 2 is going to compare to 298 other rocks. So there's going to be like a fair amount of comparison going on here. Other than that, I don't think the numbers are big. Oh, I did skip a part in the description. We're in the example, we are looking to see if they cross within a certain area between the x and y coordinates. Must be between 7 and 27. In the real one, we're looking between whatever this is, 2 something and 4 something, large numbers. Only in that space counts. So it has to be forward in time and only in that space. Okay. So let's start here. We need some math. But first we'll do some parsing. So I'm going to create a class stone because why not? Def, thunder init, woo. And we will get, let's see, we don't need view, we need line. And let's grab a line, maybe that'll make it easier. We're going to grab a line with the small numbers, not the big ones. And so what are we going to do here? We'll say like position velocity equals line dot split on this. I don't have to worry too much about white space here because I'm going to just int everything and that gets rid of it. So I'm going to say self.x, self.y, self.z, and these are like the starting self xyz, but that'll be fine. We can list map int on position.split on comma. And we really want this exact same thing. This would be self dy dx dz on the velocity. So that's basically it. I know I'm going to want a way to see these things, so we're going to make a function here that does this, and we'll return. Oh, this is a stone. It's not strong. A stone, and it's going to have self.x, self.y, self.z. All right, and then maybe like a colon, and then the exact same thing with the d, the d, z, dy, and dx. And we will close that. That'll look pretty good. So now we can come here and we can say for line. Actually, probably do this in a single line here. Stones equals stone L for L in lines. And if we run this, Python -I, day 24, example input. What did I just do? Deactivate. How do we get in that? I don't know how we got in that. Let's try that again. There we go. So let's see, what does stones look like? And we've got our stones. So the first one's 19, 13, 30, -2. It looks good. Okay. So now we have to do math. And so what I'm going to do, again, we probably don't need to do this in here, but we can say intersect self.other. So we're going to give ourselves, and we're going to, I guess we'll return a tuple. What do we need to return here? We're going to need, like this. We will define this in a bit. So first thing we need to do is there's a nice Wikipedia page for find line intersections. Where's there we go, line intersections. And sorry, this is bold and white. Um, okay. But if we zoom down here, if we can get, so if we can think about ax plus c, so for any line, right, is y is equal to mx plus b, where m is the slope and b is the initial the x position at 0. So if we can get y equals for an equation and compare it to y equals set it equal to y equals for another equation, then we can get down to here where x is going to be equal to that. So I'm going to pull this off screen, but we're going to use this as well. So we're going to say, um, let's see, I'm gonna put this in the comments here just so I don't lose it. And so we're gonna say like ax plus c equals bx plus d. And so now, we can, how do we apply this to our stuff? Well, what do we have with our starting points and things, right? So we know x is keep making comments here. X at any given time is going to be equal to t times dx plus x0, right? Um, so if we want to solve this for t, we can say t is equal to x minus x0 over dx. And that's going to be true for that's going to be true for y as well, right? So we can say it's going to be equal to y minus y0 over dy. And so by setting these two things equal, now we have an x, we can make xy. So then we can say from here, we can say y is equal to uh, x minus x0 times dy over dx, like that. And now we have our equation like that. So now, if we wanted to apply this where we set two things equal, so we could say for stone 1, where we have x will be our variable, our unknown. That's what that's of the form we're trying to get, right? That's this x here. So in this case, I guess we can multiply this through here. Hold on one second. Y is equal to x times dy over dx minus, I definitely left a part off here. This should be plus y0, like that, right? Because this y0 moves over. Minus, this will be x0 times dy over dx plus y0. So, that means to get a, b, c, and d, right, we're going to say a is equal to self dot, where are we here? Self dot dy divided by self dot dx, right? Because we're using this form right here to get to this form right here. So this a is going to be here. C is a little bit more complicated, but not too much. So c is going to be equal to, and we can just say minus self dot x times, this would be convenient, we can just say times a because we've already got this same thing. And then plus self dot y. And now we're going to do the same thing for the other rock to get the other side to get this b and d. And so these are going to be very similar. So we're going to say b is equal to other dot dy over other dot dx. And d is equal to minus other dot x times b plus other dot y. And with that, we can say we need to make sure. So what we're going to try, we're going to get to this final, did I write down the final thing? Hold on, let me grab it off the page here. The final result is going to be right here, x equals d minus c over a minus b. So the intersection, we'll say x is equal to d minus c over a minus b. If we've got that, we know y. Y is going to be equal to a times x plus c, and now it'll also be equal to b times x plus d. We've already solved to say they're the same. We also need to know the times this happened, and each rock is going to be these things at different positions, so we're going to have two different times. So we'll say t1 is equal to, and now we need to solve this equation right here. So we can just do x minus self dot x, which is the x0, divided by self dot dx, and then the other time will be the same thing, but other. So x minus other dot x divided by other dot dx, and really we just need to return a tuple here. We'll do t1, t2, x, and y. So we can, if we want to type here, we can do int, 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 int. All right. So we've done all that to get the intersection. We'll get the times, the two times, and the x and y positions where two rocks intersect. So now from here, we can come down here and we can say, let's do part 1 equals 0, because we're doing another count. No grid problem today. For I, comma, S1 in enumerate stones. For S2 in stones, and we just need to get up to I. We're gonna compare each stone to all the ones in front of it. We could also compare each stone to all the ones behind it. Doesn't matter. We're just reducing so we don't compare stones twice or to themselves. So what are we gonna say? We're gonna say, let's see. I guess we can do T1, T2, X, Y equals S1 dot intersects S2. And we can say if 7 is less than or equal to x less than or equal to, I think it was 27, and 7 is less than or equal to y is less than or equal to 27, and t1 is greater than 0, and t2 is greater than 0, part 1 plus equals 1. And that is it. Let's see. So if we run this, I'm going to get rid of my -I. Let's see. Stone has no attribute y0. Where do I do? Oops, other. Let's make that other y. That looks fine. Let's try that again. Division by 0. Okay. So we have a problem here. If a equals b, that means the lines are parallel, and we don't ever have an intersection. So we should say, if a equals b, return. I guess, does that mean we have to come up here and do, if we're going to be good, we can do from typing import optional. I think there's now a way to do this, but I don't have to do, I think there's a better way to do this now. I don't know what it is, so we're going to just do it this way. And now we better do a check here. So we're going to say result equals S1 dot intersects S2 if result is none, continue. Otherwise, that equals result. Let's try that. 2. That's the correct answer. We better grab from the. I'm gonna grab these big numbers because I hate when they do this. But we gotta change here and here. Grab you and do here and here. And I think now we can run the example, the real input. Let's see. A lot of numbers, and we got it. All right. I'm going to pause to read part 2. Okay, in part 2, I am going to throw a rock, and my rock has a starting position and velocity of whatever I want, and it is then going to hit every other rock, every stone at some point in time in the forward. So with 300 rocks, this is going to have to, so we have to figure out what that is. The input must be, it can't just be random input, because the odds that you could even possibly line all these up is very low, so they must have made it that way. All right, we'll try it. I would not know how to possibly do this without a solving package, and so we're just going to do that. So we are going to import sympy. Let's see. We can't do a global install, so we're going to do a python -m venv. We are going to source venv bin activate we are going to pip install sympy. Because newer Pythons, you can't do a global install. So we've got to do a virtual environment, but that's fine. Now, let's see, where's our part 2 here? Okay, so part 2. We are going to say, we're going to make equations, right? And our equations, we're going to do more math here. So if we have a rock with y r z r z of rock and dx r dy r dz r for velocity at t0. We know we have x r, our initial starting point, plus dxr times t. That's going to be our next thing. If we want that rock to hit one of our stones, just one stone, we're going to say that's going to have to be equal to xs plus dxs plus t. We're just thinking in one dimension. That's actually going to be, that's be true, obviously, for all the coordinates, right? So now we can say t times, we're just resolving for t here. Oops, this should not be a plus. This should be a times. So now if we solve for t by moving the t terms to each side, dividing and subtracting, blah, 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 it's going to be dxr minus dxs equals xs minus xr, like that. And if we continue, now we continue solving for t, we say t is equal to x of the stone minus x of the rock divided by dx of the rock minus dx of the stone. And this will also be true for all the other positions, right? So I can say y of stone minus y of rock over dy rock minus dy stone. And same thing for z, z of stone minus z of rock over dz. I'm doing this very carefully. Dz rock minus dz stone. And we have those equations. And so we can get rid of t now. Now we don't care about t. We have, for our any given rock, we're going to have all the r things. And so we just need to solve for the s, the stone things. So I'm going to say equation equals an empty array. And we're going to define some sympy symbols. So we'll do sympy dot sim ymbols of, and I'm going to grab you right here. These are unknown. These are basically saying I'm basically creating variables within this mathematic structure. And so we can say like that. And now we can say for stone in, let's just make it s in stone, stones, okay. eq.append, we're going to append the equation. So the equation is going to be setting this part, this right here is one equation. We're going to do the same thing with this one. We can pick basically any two pairs. The third pair is redundant in the math. So we can say s dot x. So the stone's x minus xr, the rock's x, times, we're going to do some multiplication, right? So we're going to multiply both sides by dxr minus drr to move those around. So if that's, hopefully that's not too confusing. I guess we could write this out. We could say xs minus xr times dyr minus dys equals ys minus yr times dxr minus dxs, like that. So we just multiplied both sides. And we can then actually even subtract to make this equal to 0 if we want. I think that's actually cleaner when you're using sympy. Like that equals 0. So we're going to be here. So we can just grab this whole thing. And we're going to have to make a couple changes. So we're going to append. There is no xs. There is s dot x. There is no x. There is no dyz. That doesn't even make any sense. What are you? dy stone. So this will be s dot dy. This will be s dot y. will be s dot fdx. That looks good. And then we can do the same thing here again, but changing every y to a z. So there, and there. And do we have a mess up here? Not yz. This will be zr. That. Okay, and so we're going to add all these equations. And the thing that's actually really cool is sympy is super fast. So we can say solution equals sympy dot solve equation. So we're going to do 600 equations here. We're just throwing them in here. And let's just run this with the dash I. I'm going to go straight to the puzzle input because I don't feel like we're going to go straight to the puzzle input. Let's see. Solution has no solution. Oh man, being silly. This is not solution. This is solve. It has no attribute solution, of course. So we call this, and oh, I didn't call it with dash I, so we're gonna lose this. That was taking longer than I expected. It might be. So there's some efficiencies we can do, right? And I'm thinking we can run this in reasonable time. But I do hear. Okay, so it is running. There we go. That was pretty quick. Sweet, and I've got a solution here, and so we can see if I want. So let's see, let's do assert len solution equals 1. Then we can say solution sub 0. What do we want to get here? We want solution sub 0 sub xr plus solution sub 0 sub yr plus solution sub 0 sub zr ur part 2. So if we kill this real quick, I'm not gonna run this. I'm gonna just time this just to see how long it takes. Because I think what I want to think about is, well, I'll talk it through while we wait for this. Oh, we didn't wait that long. Oh, stupid dash I killed my time. Let's see. So we're gonna run this. I'm gonna grab this time. Let's make sure we're right while we pontificate here. So we put this in here. We did get it right. Sweet. We'll go on to the next day. Looking good. But this takes about 5 seconds. Not too bad. My thinking here is for a single rock to be able to go through all the rocks. There's basically only going to be once you get to 3 or 4 rocks, there's only going to be one solution. So if we do something like that took 5 seconds. If we do up the stones, let's just like throw 5 rocks in here, right? We get the same solution in less than a second. It is the same solution, right? Yep. So 4 rocks would work. All right, let's just try this here. 4 rocks gives us the same solution. 3 rocks might not. We might not have enough equations here. So yeah, we got more than one solution here. So there's like a step we could take here where we like add 2 equations, check and see if we get one solution. If not, add some more add equations until we get one solution. Would certainly be an efficient way to do that as well. We could just leave this as 4 though and know that we get our solution in very fast time. So I'm going to call it here. Thanks for hanging out with me today. I will talk to you tomorrow. Or sometime soon, hopefully. I still owe you day 25. I'd love to say I get it done today, but I'm not sure that's true. So thanks for hanging out with me. Thanks for staying all the way to the end, and I hope you're having a good holiday. Cheers. Bye.